Okay, let's start. So again, I will try my best to do this discussion in English because we're gonna share this material over on YouTube. Right. So today, our discussion will be about pipeline processors. All right. And the interesting part about pipeline processors is that it's used by even by the most actually the top processors in the commercial market right now are all pipeline processors. Okay. But the important lesson that we're going to learn today is the following. First, you have to understand the benefits of pipeline, how to do it in general, because it's not only pipelining for processors like RISC, ARM, MIPS, or so. The concept of pipeline actually carries over for any kind of digital architecture, right? And we're going to learn how to build, in general, pipelines. You're also going to see how a RISC-V pipeline processor works. Okay, but take note, what the important thing that I want you guys to understand is the really, okay, how do you do pipelines? Okay, and why is it useful for us? Right? By the way, you guys can see the screen, right? Because I find it odd that I can't see this border anywhere. Yes, you can see the screen, right? Or not? Am I shared screen? I should be kicked. Okay, thank you, Ken. Thank you. Okay. Okay. So first and foremost, we have to discuss this thing called parallelism, right? So modern processors focus on achieving high throughput. Why? Because currently, if you go to the market and look at all the trends for Intel or AMD processors, you will see that these processors operate at around 2 to 5 gigahertz of operating frequency, right? And it's consistent for the past 2 decades, right? It's like ever since we started around the year 2000s, all the frequencies that our processor operating is around 2 to 5 gigahertz only. And then they go around somewhere in this range only, right? Now the problem is that okay, if we only have that kind of speed, technically we're not going any faster. And the reason behind that is because you see, frequency is actually power is proportional to frequency. All right, and temperature is also proportional to power. So the higher the frequency, the higher the power, the higher the temperature. And higher temperature is actually very bad for our circuits because we'll be facing things called uh, process voltage, process variations and temperature, process voltage and temperature variations. And because of these variations, our circuits tend to, they fail in their operation, right? So if you go too hot, well, one, of course, your metals start to melt. That's one thing. You get thermal degradation in your circuits. And the other one is that if it's too hot, the timings of your, RTL register to combinational logic to a register start to fail as well. Okay? And that's something that we don't want, right? But so in essence, we're hitting a fundamental limit in physics that we cannot maintain proper operation at higher frequencies because we end up at higher temperatures. So what do people do? They try to achieve, they try to replace it with parallelism. Okay. So there are two types of parallelism. One is we have spatial parallelism, which is essentially the duplication of resources. And the second is temporal parallelism, which is pipeline, okay, or reordering of operations. So we'll demonstrate that with a very, very simple example. Right? So consider the following, where you'll be throwing a pizza party over the weekend, okay, such that you have two processes. A, it takes 5 minutes to prepare the pizza. B, it takes 15 minutes to oven bake it, right? So you could actually measure your performance of making or baking pizzas. So how long does it take if you work on it alone? So like just like last week, right? And if you noticed most of our discussions, it's actually easier to visualize things by literally drawing them, right? So if you do this sequentially in 90 minutes, if you want to bake three pizzas in sorry, that's not 90, that should be 60 minutes rather. You can only bake three pizzas in 1 hour, right? So you draw it this way, right? So that's like This is equivalent to processing a single cycle processor. Now, spatial parallelism is that you duplicate your resources, right? So suppose you ask a friend who has the same skill performance to help you, right? So technically, you're quote unquote doubling yourself. So if you do that, you'll be happy because you can make 6 pizzas in 1 hour. All right. And this is what you call spatial parallelism because you essentially have two resources running in parallel, two same resources running in parallel. Right? So that's spatial parallelism. Temporal parallelism, on the other hand, is that say you don't have a friend, okay, but yourself, right? Because sometimes it's expensive to ask a friend to come over. Yeah, they have to drive to you. They have to uh, uh, prepare things just to go to you. Okay. And then say you only have yourself and you can only use two trays at a time. You can do process A and process B at the same time, actually. Okay. So say for example here, this is where you started, right? So first you did process A. Okay, you prepared the pizza, and then you start putting it in the oven. And while it's in the oven, you grab your second tray and then you also prepare the pizza at the same time. All right. And then once your oven bake is done, right, the next tray goes into the next oven, and then you start preparing the new tray. And then you carry it over and over again. So essentially, if you try to get the throughput of this process, you can bake 4 pizzas in 65 minutes, or equivalently 3.69 pizzas per hour. It's not as much, as like doing spatial parallelism. That's totally fine. But if you're limited by the number of resources that you have, so essentially, temporal parallelism processes tasks at at the same time. Sorry, at the same time. Right. So this is what you call pipelining. So temporal parallelism or pipelining is interchangeable. Okay. So that's what pipelining does. So the concept holds true for pipeline processors, or actually, I would like to say any digital process. Right. When you're computing something, let's say I have a mix of multipliers, decoders, encoders, other operations, combination logic. The concept holds true. So let's look at digital circuits as an example, right? So that we'll be seeing a bit more, a bit more on the technical aspect of this discussion. So in single cycle systems, suppose we have the path with this register to register logic, right? So you have a register here, then you have a register at the end, and then you have the combinational logic in between. So this CL here means combinational logic, right? So I just grabbed this from the Harris book, and they put this fancy symbol in it. And then, of course, we are interested in, okay, what's the maximum frequency that you can operate in? All right. And the maximum frequency of the clock, if you remember from last week, right? If you have a register combinational to register, an RTL, right? You have this clock to clock and that the maximum, or rather the clock period that you're gonna use is actually the combination of TCQ, the clock to Q, from the release of the first stage, plus all the logic in between, TL, plus the setup time by the end of the succeeding register, right? So that's how you compute the total clock, right? Now it's over here. So let's assume that the register here has a T clock to Q plus the register setup time at this other end. And if you combine them together, it's around 0.5 nanoseconds. Okay, so let's just assume that if you combine this and this term, you have zero point 0.5 nanoseconds immediately. So it's 0.5, and then you add all the combinational logic in between. And take note, you have to grab the longest combinational logic. So say, for example, 3 nanoseconds, 2 nanoseconds, and 4 nanoseconds, right? You don't get this because it's shorter than these 3 nanoseconds combinational logic. And if you do the math, you can calculate the maximum frequency of our 105 megahertz. So if you do the math, the TC over there is 9.5 nanoseconds. Very simple. So in single cycle systems, you can achieve a 9.5 nanoseconds period, which is equivalent to 105 megahertz of operating frequency. So what does this tell you? Okay. So if your maximum frequency is 105 megahertz, that also means that we can process 105 mega data samples or data data per second. Okay. So if you put some data in here, you process it, it goes to the other side. You essentially can process 105 mega samples or mega data per second. So if you think about it, if you have 5 data, you can compute it in, you can process 5 data in 47.5 nanoseconds, right? So you just throw it again. So just 9.5 times 1, 2, 3, 4, 5, you get 47.5 nanoseconds just to process 5 data in a single cycle system. Okay? All right, so very simple single cycle system. But now let's go into what if we actually make two-stage pipelines. Right? So essentially, again, pipeline is trying to do two things at once. Right? Now here's the thing: pipeline is easily achieved by inserting registers only to cut the logic. So as you can see here, we insert a register just in here, okay, in between the combination logic 3 and 4. We just put a register. That's it. Okay. Now, the thing is that we try to put registers by evenly cutting the delays, right? So, because you could argue, right? What if I put the registers here instead? Okay. Not so good, because if you put the registers in here, the combinational logic you'll get is 2 plus 4 would be around 4 nanoseconds. And then this will just be 3 nanoseconds. So that's not nice, right? We don't like that. So instead, what we do is that we try to cut the logic, right? We try to cut the logic as evenly as possible. So if you put the register over here, right, and considering the T clock to Q and the T setup time of the registers as well, you could say that the T logic or the total period, or rather, yeah, the total period that you need for register to register in the first stage is around 5.5 nanoseconds. So that's 3 plus 2 plus the 0.5 nanoseconds of the T clock to Q and the T setup time. And on the second stage, it's around 4.5 nanoseconds. All right. So the question is, what is the maximum frequency that we're going to use? Because they're using the same clock, you have to get, or you have to grab the highest or the longest clock cycle, which is 5.5 nanoseconds. Right. So for a two-stage pipeline, if you compute the frequency, you get 182 megahertz, which is significantly higher than the 105 megahertz. It's almost more than 2. It's actually even more than 1.5 times better, right? And then the way it does it is that, okay, essentially that 182 megahertz, what it means is that you can process 182 mega data samples or mega data per second, right? And then essentially, if you try to process rather five data samples, you can process it in 33 nanoseconds as opposed to the 47.5 nanoseconds of the single cycle. And then the pipeline works this way. So say you put data 1 in the first cycle, okay, it's in stage 1. This is stage 1 and this is stage 2, right? So data 1, in the first cycle, okay, it's processing stage 1. But in the second cycle, right, you are processing stage 2 and stage 1 at the same time. Okay? So essentially, you are pipelining at this moment. And in the next cycle, okay, that stage 1 moves to stage 2, and then you're immediately processing stage 1. The new data, stage 3, goes into the stage 1. In the next cycle, this stage 1 moves into the stage 2, and then you process data 4 in stage 1 again. Okay, so essentially, you are already pipelining at this moment. And look, you have significant speed up, right? Because you're now processing 5 data in 33 nanoseconds rather than processing 5 data in 47.5 nanoseconds. And from your lessons last week or the previous week, you can actually compute the speed up. So if a single cycle takes 47.5 nanoseconds to process 5 data, but the two-stage pipeline down here, right, takes 33 nanoseconds to process 5 data, you essentially get the speed up of 1.44. And to get that, you get 47.5, the longest time divided by the shortest time. You divide that and you get 1.44. So you have that number of data being processed at the same time. Okay. And as you can compare over here, right? Actually, I should have put the time, real time over here. It's like 9.5. You have 19 over here, to 47.5 nanoseconds. No, I probably should have drawn this better in the same time scale. But that's totally fine. Okay. So visually, you could see that, hey, because I am pipelining operations, I am technically doing parallelism. Well, it's not technically, it's actually parallelism. So let's do it a step further. What if we do 3 stages? Again, we can add more pipeline stages while trying our best to evenly cut the delays. So in your homework, there's a very interesting challenge there, is because you have this machine learning processor that does multiply and accumulate operations, but then how do you pipeline it properly? Okay. So take note. That's why I'm repeating the evenly definition over here, because I want you guys to realize. Now, for the 3-stage pipeline, well, you don't have any other choice, but you have to pipeline all processes by cutting the combination logic in between. Right. So insert registers here and here. Okay. Now, in the first stage, you actually have to insert a register for the combinational logic 1. Actually, you can combine it just to one register over here. Totally fine how you want to represent it. But the point is that because these two are operating in parallel, well, technically you could say they're spatially in parallel, right? You have to put a register in between. Okay, one up here and one down here. Okay? And that's totally fine because later on the output will be sent to the second logic. Okay? I'll erase this again just to make sure it's clear. Over there. Then if you calculate the logic delays needed per stage, again, in stage 1 you need 3.5, that's 3 plus the T clock to Q and setup for the registers. In the second stage, it's 2.5. And in the fourth stage, it's 4.5. Right? So what's the maximum period that we need? We need, or rather, what's the minimum period that we need? We need a minimum of 4.5 nanoseconds. Right? Because that's the proper way, or rather, that's the amount of clock that we need to properly process the third stage or combinational logic 4. Totally fine, not a problem, because the previous one was using around 5.5 nanoseconds. We're still getting a bit of a 1 nanosecond speed up there. So if you calculate the maximum frequency, you get around 222 megahertz. And that means you can process 222 mega data samples per second. And if you draw the pipeline, it's over here. So you can actually process 5 data in 31.5 nanoseconds, right? Just down here. Okay. So again, just to make sure you understand and just to repeat the discussion. So data 1 goes into first stage, the first cycle. In the second cycle, stage 1 passes it on to stage 2 over here, right? And then data 2 is already fed into the first stage. And the third cycle, stage 2 is passed on to stage 3. Okay. And then stage 1 is passed on to stage 2, and then the data 3 comes into stage 1. And at this cycle, the third cycle, you could see all 3 pipeline stages, all 3 of these, stage 1, stage 2, and stage 3, are all working on something at the same time, all in clock cycle 3. So essentially, you are parallelizing operations at the same time. Okay, so that's pipeline. So it's a bit of an improvement overall, but it still pushes performance in the long run. All right. So here's the thing. Essentially, pipeline in a nutshell is simply you're trying to do 2 things to improve your performance. One is that you cut the logic to increase maximum operating frequency. And the second is that you're temporarily parallelizing the operations. Like in here, you're doing 3 things at the same time. Okay? So that's parallelizing operations. And take note, that's 3 different operations, right? Because they have 3 different combinational logic delays. And if you add both, you get super performance. That's what pipelining is. Okay? So now, take note that if you observe the pipeline of the 3-stage process, observe that the pipeline actually takes x minus 1 extra cycles to fill up the process in the first instruction, right? Look at that, right? It actually takes stage 1 and stage 2, okay, extra cycles at the very beginning only, just to process data 1, okay? And then on the third cycle, okay, on the third cycle, data 1 is complete. But then, after the third cycle, every succeeding cycles, right, suddenly data 2 is complete, data 3 is complete, data 4 is complete. The drawback for pipeline stages is that you have this x minus 1. Actually, I'll replace that with k minus 1 later on. All right. You have this x minus 1 extra cycles just at the beginning. All right. And then if you're only running very few data samples or few instructions at the beginning, that extra delay becomes significant. Okay. Okay. What did I do here? Whoops. Yeah, it's the same thing. I just replaced that k with an x, x with an k. All right. So k here is the number of stages. Right. So if you have a 3-stage pipeline, you need 2 extra stages at the beginning. If you have, say, 10-stage pipeline, you need 9 extra stages at the beginning just to fill up the pipeline. Okay. So that's just the drawback for pipelines. But usually pipelines, we don't go to 100 stages. No, no, no. It's just probably in general around 15 to 20 for our commercial pipelines, or rather our commercial processors. Okay. So it's just something to take note of. Now, that extra delay at the beginning becomes significant to some degree. Okay. So it takes k minus 1 exacycles at the start upon reset of your process, but it takes 1 I cycles per instruction after. Actually, this is I cycles uh, per, okay, if I here's the number of instructions or data, instructions, after the startup cycles. So say, for example, it takes a total of k minus 1, which is 7 clock cycles in total to process 5 data, right? Because you have 5 data, that's like that's your I, okay? I or D, or I put I because we're going to use I as instructions later. So you have this 1, 2, 3, 4, 5, right? But you need the 2 extra cycles earlier, the k minus 1. Right. So in total, the CPU just process time is 31.5 nanoseconds. You just have to add this C total, which is the total number of cycles, which is k minus 1 stages plus I number of data that you have to process. Okay? So that's pretty much it over here. But eventually, at some point later on, the startup cycles don't matter anymore if you're running a gazillion number of cycles for the data. That means, what if I, the number of instructions or data that you're processing, becomes infinite? Okay, it's very, very large. So yeah, sure. Let's say, for example, in our 3 stage pipeline, so this k minus 1 is actually 2. But if you're running, say, 10 to the 6, a million data, okay, technically 2 plus 10 to the 6 is just still 10 to the 6 cycles, right? So that's pretty much it. So essentially, later on, pipelines actually try to achieve a clock cycle per instruction of 1. So after the first instruction, right, or rather after the first data being processed in the succeeding cycles, it takes only 1 cycle to process the succeeding data, right? So you can see it that way. So let's try to compare two examples, right? What if we're not running a gazillion number of data, right? So the single cycle, the one that we processed earlier, is just running 5 data from startup, right? Just from the very beginning. Okay, so a single cycle takes 47.5, 2-stage 33, 3 stages 31.5, right? And if you compare it, if you compare the 3-stage with the one single cycle stage, these two, you get a speed up of 1.5 times only. But if you compare the 3-stage pipeline to the 2-stage pipeline, you'd still get speed up, but to like 4% increase only. That's not so convincing, but it's still a speed up, right? Now here's the thing, right? As mentioned earlier, if the startup cycles don't matter anymore, if the number of instructions or the number of operations that you're doing is much, much higher, let's say for Intel AMD processors, it uses around, let's say, the minimum 14 stage. Okay. And say we run 20 instructions, that's a total of 33 cycles only. But if you run a million instructions, that's like 13 plus 10 to the 6, that's approximately 10 to the 6 still. Because again, I'll reiterate that pipelines try to achieve a clock cycle per instruction of 1 per cycle. Okay? Cycles per instruction. That's what CPI means. So if you compare it, what if you say 10 to the 6, right? What it approaches to is that the operating frequency that you're approaching, or rather the operating periods that your system has is around this. And if you try to calculate the execution time for a million instructions or a million data, it's also the same. Technically, it's just the same. It's equivalent to the frequency that you're operating. Okay. And if you calculate the speed up, let's say you compare two stage to one stage, right? You get around 1.72 times improvement. If you compare three stage to one stage, you get 2 times improvement. Now, this 2 times improvement is realizable only if you run a million instructions, right? This 2 times improvement, you could see three stage versus one stage, as opposed to the one earlier, three stage versus one stage of 1.5 times that only processes 5 data. Now that 1.5 times is only happens if you're processing very few data samples in the beginning. But if you're processing a million instructions or a million data, you get that 2 times improvement, right? And between three stage and two stage, you get the 22% increase as well. Okay. So essentially, when you're running a million instruction or a million data, what happens in your pipeline is that you're getting the benefits of cutting the logic into smaller clock cycles, or rather into smaller periods, right? So you can see that immediately at the end. Okay? That's why pipelines are very, very, very. All right. Do you have any questions here? That's a very good 30 minutes discussion. We have now the second 30 minutes, which is a much more exciting. Before I proceed, do you have any questions at this moment? No questions? Okay, we can proceed. Do the homework. It's a very interesting problem. Very easy to do, but it's something, it's a puzzle that it's for you to solve. Okay, and it's actually a very practical problem, when, especially when you're dealing with AI or machine learning processors. Special mention to Ray, if you're gonna do vector processors, uh, if you try to look at last year's 199 process implementation, he also did pipelines. Okay, so if I'm not mistaken, he did pipelines. So it's something to consider. All right. So we'll proceed to how do we design a RISC-V pipeline. And take note, we're focusing on the core RISC-V processor, not any other extensions attached to it. Okay. Now, designing a pipeline is easy. Also, by the way, Ken, just in case, right? Pipelines are important for what you're gonna do later on, in case you're gonna proceed with RISC-V pipeline as well. Okay. Uh, so designing a pipeline is easy, as you've seen earlier. You cut the single cycle system into parts. So this is your single cycle system. Cut it, you cut over here, you cut over here, and then just insert registers. Did we change anything with the combinational logic? Nope, we did not change anything. It's just get the single cycle, cut it to stages, and then insert those registers. Done. All right. So the RISC-V pipeline, step one, grab your single cycle RISC-V processor. Okay, extend it a bit because we're gonna insert sections later on. Cut it into parts, into the 5 steps that we always discussed in the previous lectures. We had the fetch, decode, execute, memory access, and the write back. Right? And then you insert registers. And then you're done. All right? That's it. You're totally done. Okay? But the thing is that one thing to note, especially for those taking who are for the ones taking this CoE 113 class, is that you actually have to how do you put this? Label those registers in between, like to indicate, hey, this is the decode stage, this is the execution stage. They have the same name, but they just appended last letter at the end, just to indicate what stage is this register placed actually. Okay. So you're gonna have to do that later on in your MP, which we will release probably in a week or two. Right? And then just make sure the naming convention is consistent. So there, you already have a pipeline. That's it. Right? Now you might ask, what about the pipeline control? Do we need an FSM just like the multi-cycle last time? Nope. Quick answer, no, you don't need to design a finite state machine. What you can do is just simply reuse your simple single cycle controller and then you pipeline it. And what does that mean is that there, you grab your single cycle controller, same thing, you just have to make sure the labels of those wires are consistent. and then you pipeline it per stage, right? You just pass it along the pipeline stages. Take note, as you can see over here, some pipeline controls, or rather some of the controllers disappear as you go into the subsequent stages because you don't need the other control signals. For example, from this stage, this is the decode stage, right? This is the decode. By now, you should be familiar by fetch, decode, execution stage, memory stage, and then the write back stage, right? In the decode stage, okay, you release all the control signals, not a problem, but the IM source over here is only used in this stage because the extension, the immediate extension is over here, in the decode stage. But when you move into the execution stage, you could see that IM source is not there anymore. Why? Because you don't need it further for that part. In the execution stage, you need the jump, branch, ALU control, and ALU source control signal. But in the when it gets into the memory stage, it's not there anymore because you don't need it anymore. But is there any change along the path? No. They're just disappearing as you go to other stages. And you literally just need to recycle the control unit that you had in your single cycle processor. So it's a big hint because when you try to make your pipeline, all right, the pipeline that you're making is that you're just inserting registers in between. There's nothing else that you need to do. Well, actually, in the next discussion, we will have to deal about hazards, which we'll discuss in the next meeting. Okay. But as for the moment, to design the pipeline register or the pipeline RISC-V, again, just insert registers in between, and that's it. You don't need to do anything else. Okay. So let's see what happens in a simple add instruction, right? And here, this thing becomes interesting. So follow along with me again with trying to process how the pipeline uh, is processing signals because it gets really interesting in the succeeding slides. So first step, fetch, right? So you just fetch, right? The program counter is updated, and then the program counter fetches the instruction and then stores it into the instruction D register. That's it. And then here's the thing, right? Be mindful of which resources are being used in each stage. But here's the thing, and it's very cool because if you try to go back to your single cycle processor again, right? It's just literally cut. It's using the same signals, but you just cut it into different pipeline stages. Okay. So for the first stage, you need the program counter and the instruction memory, right? And of course, the one that updates the program counter. In the second stage, for the add, we're just focusing on the add, right? When it gets to the decode stage, right here in the middle, all of these signals are being used, right? The RD, the RD1, 2, the control signals that you need, so on and so forth. Technically, you don't need the IM source at this stage. Doesn't matter because the control signal that you're using at this stage is not really doing anything to the immediate extension because we don't need it, right? Now, take note of the important control signals that we're passing through. Actually, have to pass through all. Yeah, but for the purpose of analyzing the add instruction only, you just have to take note of these highlighted ones. The reg write, which is eventually we'll get into the final stage for the write back stage here. Right? You just prepare the control signal at this stage. Okay. The ALU control, ALU source D, totally fine. Pretty much which you need in the next stage. Okay. So just pay attention to the control signals that you need. And again, whatever you use for the single cycle, it's the same thing. Okay? When it gets to the execution stage, that AL control D moves into AL control E, AL source D into AL source E, because it's the one that controls this multiplexer and the operation the ALD. Done. Right? And then, of course, the data that you read earlier gets transferred. The R destination gets transferred as well. Totally fine. Okay, so I'm not discussing these bullet points here anymore, pretty much because I just put it there for you to read in case you just want to read this instead of going to the lectures, to the video lectures. But the point is that, hey, these are the control signals that we are running. Okay. And then on the fourth stage, we have the memory access. You pass on the reg write, which controls the write enable signal. Totally fine. Result source, we're going to use that for this multiplexer. Since it's not being used, take note, okay? the control signals that are not being used at the stage but are needed later in the stage, we are just passing through. Okay? They are just passing through. And here, look, what happens? The ALU result, it's not needed by the data memory, you just make it pass through. The destination register, you just make it pass through. Essentially, for the add instruction, normal register type instructions, memory accesses are not useful, but you have to pass through them. Okay? Unfortunately, you have to pass through. And then the write back stage, finally, because this reg write is activated, because we need to write back into the register file. And take note, that reg write came from here, came from the previous stage, and came from the original decode stage, reg write D. Okay, as well as the result source W came from here, the previous stage, and it came from the decode stage as well. So you passed it along the pipeline all throughout. Okay. And actually, I forgot to indicate this guy, the destination register. Yeah, it should be highlighted too. Sorry about that. So that completes your entire add instruction. Okay, so let's try one more, actually two more if I'm not mistaken. Yeah, two more. We're almost done. Okay, what about the load word instruction? Okay, so follow along the lines. So load word, fetch, not a problem. Decode, just take note of the instruct control signals that you need, but this time take note that we're also accessing the immediate field of the instruction. That's how it happens in the decode stage. In the execution stage, these are the control signals that are needed. Take note, it's a load word, so control E needs to be 000 to do the add operation. Grab the RDE, do the immediate extension over here. All right. Memory access, that's the time when the memory is being used. Okay, so the memory access is important for the load word, but again, take note of the register signals that you're using, or rather the control signals that you're using, right? You're passing on to the destination register, not a problem, and then eventually blem. Okay, so again, I forgot to highlight the destination register over there. Okay, so you're just writing back. It's almost the same thing as the add. Okay, but did you have to worry about the control signals? No. So again, it's so easy to do a pipeline because of the complexity of having to design pipeline register. This pipeline stages or pipeline processors is so easy to do. People like to do it because you get the benefits of speed up. Okay. All right. So that ends for the load word. I'll leave it up to you how to analyze. It's up to you how to do it because I think it's very straightforward to practice on your own how to draw these control signals, right? You just practice it on your own. And you can do it on your own, right? All I've done so far is just to demonstrate for you, hey, this is the figure that you need. It's so easy to draw all those signals. Now here's the exciting part. We're gonna check, we're gonna see how pipeline is done in action. Let's say for this 5 instructions, all right? And take note, I've color-coded all those signals, all right? And then we'll trace what happens to the pipeline, all right? Okay. After the last after the last store word, rather, assume not instructions follows, or we're just doing nothing after it. So we're just gonna ignore what happens after the store word. All right. So let's go it one by one. Cycle 1, the load is being fetched. Cycle 2, oh, I did not copy. I should have copied these things in here. Okay. But take note, load word, add, store word. Hold on. Let me edit that very quickly because I want to make sure it's understandable. Oh no. Never mind. I won't edit that anymore. Okay. Yeah. I want to edit that instead. Very, very quickly, guys. Hold on. Uh-huh. I'll copy paste that. I'm gonna paste it up, not there, but here, so that we have something to trace. Oh, we have something to look at while we're going through the discussion. Put you up here. Whoop, whoop, whoop. Okay, we're done with that. Going back. Okay, quick edits. Alright, very cool. Okay, just to trace. Okay, so first instruction, fetch. We load word. It's the load 1 fetch. Not a problem. Second cycle. Load 1 moves into the decode stage, and then the second load is in the fetch stage, right? Third cycle, the load earlier is now in the execution stage. The load 2 earlier is in the decode stage, and then the new instruction add goes into the fetch stage. Cycle 4, the first load, okay, is now in the memory access stage. So this is load word 1, load word 2. This becomes the add, and then we have the add I, right? So I'm just highlighting the control signals and the data, the important control signals and the data that we need. Okay. In the fifth stage, it's the same thing, right? Oh, I did not copy paste that. In the sixth stage, right? Oh, in the fifth stage, the entire pipeline is filled. Okay. So you have actually have the store here. You have the add I over here. You have the add, the load word 2, and the load word 1. And look at that. Load word 1 or has finished already. Okay? It loaded the data that it needs for the system, okay? Because it's in the write back stage already. So in the next stage, you will see that, okay, the load word 1 finishes, but all the other operations are continuing. All right? There. And of course, I mentioned earlier, nothing follows the store word. Nothing follows over here. So let's just say it's empty. And then essentially what's happening is that we're just finishing the pipeline. Stage 7, you could see that the add is here already. The previous load word here in 6 is at the write back stage. So in the cycle 7, it's done. Right? Add I over here, and then store word is here. In the next cycle, add is done. Right? So this is the add I, and this is the store word. And the next cycle again, you just have store word. Technically, store word is still processing here, right? But essentially, the store is not doing anything because by the store word, okay, if you go back here, store word actually finishes on the fourth cycle, right? So even though you pass anything onto here in the next stage, there's nothing being done. Okay. That's why in the cycle 9, store word is finished. Although it sort of is, store word is still quote unquote processing in here, but it's not doing anything at all. So that's the beauty of the pipeline. So let's go back again just to see the animation. All right. So look at that. So stage 1, you can see how it's filling up the pipeline per stage. Right there. Fantastic. Right. And then as you're going along the cycles, it's just finishing all the pipeline stages until you're done. So that's how cool pipeline is. Okay, dokie. So in summary, right, is that pipeline so cool? And it's very, very interesting because you could do so many things about it, and it pushes performance to the next level. If you can't pay for extra area in your chips, right? Because sometimes, let's say you have a machine learning processor, so you have a Mac unit over here, you have a Mac unit over there, right? You have a Mac unit over here. For if you do spatial parallelism, totally fine. This gets you the best performance increase. That's why in your processors, let's say you buy the current what's this, the i7 12 something K models of Intel, you would see that they have around 12 cores in parallel. So it's like having 12 processors running at the same time. Okay, but the thing is that okay, it's expensive because space is translated to costs, right? But if you do pipelining, instead of having multiple maps, what if you can do, multiply and accumulate at the same time? That's pipeline, right? It's a pipeline. You may not get the same benefits of spatial parallelism, but hey, I'm still able to get through better throughput through temporal parallelism or pipeline. However, there is a problem here. Nothing comes for free because pipelines suffer from data flow hazard where timing is critical. And that's something that we'll discuss more in the next meeting. Okay? We'll discuss more about hazards, which needs to be handled, although it's very easy to handle them. There are very specific scenarios already. But complicated pipelines like those of AMD and Intel are, they have even more sophisticated hazard control. Okay. So time check. Perfect. It's like around 45 minutes only. All right. So any questions here? Have any questions? Are pipelines so cool? Yes, Tim. Yeah, while you're typing your question. Does the first stage start at the PC MOOCs of the instruction memory? What do you mean? Does the first stage, this one, start at the PC MOOCs? Do you mean because there's a register also in the PC? Well, I mean, that's a good question. Okay. Okay. Sige. Let me think about how to answer that. Technically, the entire thing here is the first stage. Okay. So it's like you could treat this program counter in the first stage like the second stage decoder. Oh, sorry, yeah, the decoder, right? Because this is also a register. So essentially, the first stage is including the program counter already. Okay. So you don't count like first stage from here. No, no, no. The first stage is technically from here, this output of the instruction memory. Because this entire thing here is or rather, it starts from here and it ends over here, right? Okay, let me redraw that. Sorry. So it starts from here, technically it ends from here. But I guess the proper way to think about it is that the entire first stage is this entire block just before this pipeline register. Okay, Doki? So it's not because of there's a register in here. All right. So that register, that program counter is part of the fetch cycle. Okay. Just like here in the decode stage, right? In the decode stage, that register file, technically, this is still a register, right? It's still part of the entire decode cycle. Okay? I hope that answers your question. But bottom line, you have to consider the entire thing here as the fetch stage. Okay, Doki? That's a good clarification, good question. Any other questions? Okay, so after the first clock cycle, nasa decode stage na yung first instruction. Yes. Okay, perfect. That's correct. Okay. So going back here, I'll write down. Okay. So here, all right. The purpose of this program counter after the first clock cycle, right? So this is, let's say you're processing address zero, kunwari, right? Or program counter zero. Okay. So after the first stage, right? Or during the first stage, program counter is zero, right? And then it already tries to load the instruction memory. In the next stage, bam. Okay. That instruction here, this instruction here, let's write it instruction program counter zero is processing or it's holding the instruction zero. But in the next stage, right, here you can see here, right, you're already preparing the PC plus 4. Right? So in the next stage, okay, this program counter is already pointing to PC plus 4, which is the load word instruction up here. All right. So that's how it's processed. Okay, I hope that answers your question. Or do you want me to repeat it? Okay, fantastic. Perfect. Okay. How about the others? Do you have any other questions? Yeah, it's confusing at first, but my suggestion is that you go back here. Again, our technique, you make the drawing, right? And then try to trace the signals from here onwards. Okay, so it gets time to get used to it, right? But I guess the best way, my best technique for you is that you have to consider that. That's why I made a note somewhere above. Yeah, yeah. If you go back anyway to the very, very first slides of the add instruction, I did note that you have to take note of the resources that are being used in the stage. Okay? So I guess one way to think about it too is that just to identify what are the pipeline registers in here. Okay. So there's a new question. The registers per stage di sila dikit implementation-wise, right? It's like a separate set of registers in parallel. Yes? Uh, Good question, Ken. Yes, they are. Actually, I will leave it up to you how you want to do that. Okay, so Ken's question is something like, isn't this just one register? Do I treat this as one big register that are concatenated to each other? Or do I treat it like separate registers at the time? Right? I have a register for reg write E, register for result source E, register for write mem E, as opposed to one big register and then you're just combining it into one. Quick answer, Ken. It's up to you how you want to do it, right? I've seen some people just make one big register, right? So if you're gonna code it, it's something like you make separate register, like say write reg E, reg result source E, or reg mem write E. Okay. That's totally fine. You could do it this way. But some people do it this way. Like you have wire reg write reg E, wire result source E, wire I don't know, mem write E. And then they just have one register that's very large. And it's gonna call it the what, exareg. Okay. And then what you do is that you're gonna concatenate all these wires. Right wire E, RSE. You're gonna concatenate that into this exareg, right? Exareg. That's totally fine too. Okay. You could do this implementation or you could do this implementation. Doesn't matter. Okay. So it's a pros and cons of which one that they have to watch out for. I would personally do this, that what Ken is suggesting, as opposed to this, because for the practical reason that if you do this, you are more prone to error because you're trying to write down too many things. Okay? But it does look more organized as opposed to this. Okay? So it's up to you. Parang ang hirap i-track nung latter unless you flood it with comments. Yes, practically it is a bit more uh, difficult to track, but it's more. Actually, I've seen this style, but it's technically it becomes more organized. Okay? I would say either way, it's gonna be difficult to track, but you have too many signals on the latter one. But on this earlier one, it's much more simpler. Uh, it's less organized than this other one. Okay. Because in here, you have the advantage of writing it into a single wire. All right. So, yeah, you can do that. Instantiation would be a pain for the first one. Yes. But I'll leave it up to you how you want to do it. I have seen people do something like they made this into one module, right? And they did this first part, but they made it into one module. And then on their top module, they just call this first module. Actually, I did that in my previous project when I did this back in CoE 113. And I mean, it was fine, but I figured that, hey, this is actually more organized. It's up to you guys. Okay? I'll leave it up to you how you want to work on it. All right? Would it help if nagawa na yung multi-cycle ME before doing the pipeline? I don't have a multi-cycle ME. Okay? After the single cycle ME, we're going straight to pipeline. All right? Because if you go back into the multi-cycle machine exercise, or rather, if you're gonna do the multi-cycle machine exercise, it's nowhere near the single cycle nor the pipeline cycle. Nor the pipeline cycle. What pipeline RISC-V processor? No, 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 no. I'm not doing it. I'm not gonna trouble you with that. I mean, it's gonna be a good exercise. I hope. If you give, if we have time later on, maybe our last ME would be the multi-cycle rather than the pipeline. Because making the pipeline is just single cycle and cut it with pipeline stages. That's it, right? That's the only thing you need to do. But you have forwarding mechanisms that you have to consider, which is discussed next week. But no, I did not put the multi-cycle anymore because it's a nice exercise, but it's totally different from the single cycle and pipeline cycle processors. Okay. because you have to make a state machine. Although that would be a very nice uh, um, exercise. I'll think about it. Maybe I could make the the an additional that if you make the multi-cycle together with the pipeline, you're perfect already in the lab. Parang mas madali siya nung 105 pero nakakalito ngayon sa 113. No, because in 105, the multi-cycle processor that you're doing is the Marie. It's a completely reduced multi-cycle processor. Right? It's nowhere near RISC-V processor at all. Okay? It's using a different instruction set, and then there are many operations that were reduced. Okay? And it becomes a multi-cycle because I'm just gonna redraw it here. Where did my pen go? Okay, I'm just gonna redraw it here, but or let's look for an empty space. Yeah, I'll use this empty space. The Marie multi-cycle processor actually uses, oops. The interesting part about the Marie multi-cycle processor is that you have a single, you have the ALU, you have the memory, you have the, what else do we need? We have the register. Okay. And then all of them are sharing the same bus only. Okay. So you needed an arbiter or multi-cycle arbiter, okay, to control how they're going to use that bus. Okay. So let's say call this the control. Okay. So that's why you needed the multi-cycle. If I remember correctly, that's how the 105 was done. Okay. Time check. Any other questions? No more questions. Those are very good questions. I'm happy that you're interested in the topic. So next week we'll again discuss about hazards. It's probably take an hour as well, but probably less. But it's very very minor only. It's something that we have to watch out for pipeline processors. Okay, and yeah, thank you for attending. And if you have no more questions, I'll see you on Friday. Okay, so I'll upload this discussion in YouTube again. Okay. Thank you so much, and I'll see you on Friday. Bye bye. Thank you. Thank you.